Hey, hello, workshop group. I've got a question about your new material. It looks like this is on equilibrium stuff, and it's called the torque on a tall cabinet. But before we get to a cabinet, let me just point out if you have any object and it's going to be stationary, that means it can't accelerate. But that is both translational and rotational. So whatever the shape or size of your object, if it's going to be stable, like a building or a bridge, or in this case a cabinet, regardless of its shape, you want the acceleration, the translational acceleration to be zero, and the rotational acceleration to be zero. That way, it won't translate and it won't rotate on you. And of course, Newton's second law for translational motion and Newton's second law for rotational motion are really saying then that this the translational acceleration is coming out to be zero. And of course, when rotational acceleration comes out to be zero, these are what we call the two conditions of equilibrium. Now, this is really a vector, and I guess technically this is two. But as we're learning to go along, if we just kind of keep it as simple as we can, kind of two dimensions. So if I take this cabinet, the cabinet could move left or right or up or down. So when it comes to translations, we're really looking at forces in the x direction and forces in the y direction. And if you only have forces in the x and y, then that can result in a rotation around a z-axis. So those are our options if we leave it just to a two-dimensional plane. Clearly, in a more complicated world, we can have rotations a translation in the z-axis, and therefore we can also have rotations around a x-axis or rotations around a y-axis. So that would be the kind of the more general statement. But again, as we're just kind of learning more and building up, let's just eliminate the translation in the z, which then eliminates a rotation around an x or a rotation around a around a y. And so these are our three equations, although we still call them the two conditions of equilibrium. All right, so let me use that phrase. The two conditions are equilibrium. That is, all the forces have to add to zero, and that really results in two equations because we don't want it to move left or right or up or down. And then, of course, we don't want it to rotate around that z-axis. And so these are the two conditions of equilibrium, and then these are the three equations that we would apply. Okay, keeping then that in mind, then let's look then at this particular problem. Maybe I'll get myself a fresh sheet now that I kind of gave the general idea. Let's take this cabinet here. All right, so here's a cabinet. And maybe I'll start with a cabinet that is not being pushed. And so if you do a free body diagram here, the center of mass, mg, and I'm just going to put it right at the center of the object. I know not all cabinets have their weights evenly distributed. Many cabinets, when you pack stuff, you put the heavy stuff down below and the lighter stuff up at top. And even sometimes you put the heavier stuff near the edge where you can reach in. And so the center of mass isn't necessarily the center of the object. But I think we can conclude, let's see, how does he write this? It says a tall cabinet with 2 feet has a mass of and a height of and a width of. It is pushed with a horizontal force. If it is applied to a height greater than the ground, the cabinet begins to tip over. Yeah, it should be a little clearer that there should be like a word uniform in here, a tall, uniform, rectangular cabinet or something. But I can see in his picture he's got the force of gravity right at its center. So up, down, and left and right, this is the center of gravity. So that's why we did that earlier chapter. I guess that was chapter 9 stuff, the center of mass. So that would be pulling down. And then it says the cabinet has 2 feet. And so there would be a force which we'll call this foot number 1. So your author calls it F1. And then there'd be another force on this foot. Let's call it F number 2. Now, again, ignoring the sideways push for just a second here, hopefully you can see here that F1 needs to be equal to F2, and they each need to be equal to half the weight. I say that because remember this condition of equilibrium. This condition of equilibrium says that the sum of the forces in the y direction have to be 0, because if it's not, it will accelerate. It'll go up or down. So if the cabinet's just sitting there and nobody's pushing on it, there will be these 2 forces, and those 2 upward forces have to equal the downward force. Now, that alone doesn't say it has to be half. That just says that F1 plus F2 equals mg. Okay? Oh, but I get the fact that they each have to be a half because of the other condition of equilibrium. That's the torques. And so if you think of the center of mass maybe as its pivot point, the force number 1 would be pushing it and rotating it in a clockwise direction. And force number 2 would be pushing it in a counterclockwise direction. And so I'll call that torque 1, but it has to equal torque 2, or at least in magnitude. Maybe better put would be torque 1 plus torque 2 has to equal 0. Okay? But looking at the magnitude then, and of course remembering torque, there's a couple ways we can calculate torque. This is one thought process. I'm going to use this where the r and the sine theta are grouped together. We call this the lever arm, r perpendicular. And so in my case, if I draw a line going up, the perpendicular distance to that line is half the width of the cabinet. So torque number 1, using the perpendicular distance, would be half the width of the cabinet, and then it would be force number 1. Whereas torque number 2 over here, if we draw a line upward for number 2, that it would also be half the width of the cabinet if the center is the center of mass. And that's, like I said, something we're going to have to assume in this problem. But this would be, again, a W2 and a force number 2. Now, technically, these are their magnitudes. See, because torque number 1 would rotate it clockwise, so usually that's labeled with a negative torque. And so number 1 here would be a negative torque, and then number 2 would be a counterclockwise, so it would be a positive torque, and so the 2 torques have to add up to 0. That's how I know their magnitudes are the same. And since their distance is the same, this would conclude, once you say the magnitude of torque 1 has to equal the magnitude of torque 2, and the center of mass is right in the middle, then you conclude that magnitude of force 1 equals magnitude of force 2. And that's how I got them to be half of the weight. And so this would be what we would call a symmetric case, where the simple case is that these 2 forces, they're both equal in magnitude, they're both up, and the 2 supply an upward force, and one supplies a negative torque, and the other one supplies a positive torque. So that, again, these 2 conditions are met. That is, the sum of all the forces in the y direction come out to be 0, and the sum of all the torques around a rotational z-axis come out to be 0. All right, again, haven't really got to the problem, but this is kind of more of a lecture here of, okay, so what is happening with a cabinet that's just sitting there? Nobody's pushing on it. Okay, well, here's where it gets more interesting and more complicated, is when somebody pushes on the side of the cabinet. All right, so I've got the cabinet here. And again, doing a free body diagram, I would have this downward force mg, and I would have then this upward force F2, and another upward force, which your author labels it as a little smaller in size. And here's why. If I then take this push, and maybe I will change my thinking for a moment. Let's think of it as pivoting around this corner instead of what I did in kind of a general look of a cabinet. I had it pivoting it around its center. Although if we were to come back to this picture and say, let's look at the pivot around here, and ultimately that's what I want to do, because the question is when it tips over here, okay? But right here, if I were to do this same problem, but think of this as its pivot, then I would have a torque from gravity making it rotate in a clockwise direction, and a torque from force number 1 pushing it in a clockwise direction as measured from this point. And again, those two torques would have to be equal. So maybe I'd write it this way. The magnitude of the torque by gravity would need to equal the magnitude of the torque from number 1. And see, the torque from gravity, using this equation again, would be the perpendicular distance. So that would be half the width. And its force would be mg. Whereas the magnitude of the torque from number 1, thinking of this as the pivot, would be the whole width and force number 1. And if you cancel off the widths, you can see that force number 1 has to be mg over 2. So that's another way of getting what I had done earlier. And maybe I should have done it that way, only because that's ultimately what I want to do for this problem, is to think of it down here on this corner. So remember, we can think of it from any spot, because the truth is we need the sum of the torques to be 0. There it is, sum of the torques to be 0. Not just from its center, but from any point you can think of, because if it didn't come out to be 0 for some point, then it would rotate around that point. And so when we say our conditions of equilibrium, this is condition number 2, the sum of the torques is to be 0. Remember, we're also really saying it's the sum of the torque needs to be 0 around every point, not just one point, but every point. Because if there is a point where it doesn't come out to be 0, then it would rotate around that point, and we want the thing to be in equilibrium. So feel free to pick any point you want. And that's kind of what I'm doing here, kind of backpedaling and saying, look, I did the torque around the center of mass just to kind of get the ball rolling here. But when I started to do the problem, I realized that I probably would be better off doing this corner. And I'm now trying to say, look, you can do that. You can take it around any corner or any edge or any center or any place you want. The torques have to come out to be 0. If some of the torques don't, then it would rotate around that point. And we want to make sure it doesn't rotate at all, meaning it doesn't rotate around any point, not just one point. All right, so you can see you come up with the same thing. And if you wanted to find then F2 using this method, you could either then go to condition number 1, where it says the sum of the forces have to add up to mg, and conclude that mg over 2 is also F2. Or you could pick this foot over here, foot number 1 as the pivot, and kind of go through the same logic and get the same thing for F number 2. So whichever way you want to get it, you're going to come up to the same thing, that F1 and F2 are equal and they're half the weight. Whether you pick the pivot point to be the center or foot 1 or foot 2, it doesn't matter, okay? So that's kind of an interesting way of trying to emphasize to you that I can pick any place I want. And I'm going to come back to the problem here and pick foot number 2 here. And this is why I got sidetracked, the author makes a force number 1 a little bit smaller in its diagram, because if you think about this as the pivot, then you can see here from the force of gravity, that would be pivoting it in a clockwise direction. And this force from this outside, let's say it was a person pushing on it, and see, the problem just says it is pushed using a horizontal force. So they give this as a 146. But using this as the pivot, this would be pushing the cabinet in a clockwise direction. But also the force from foot number 1 would be in a clockwise direction. And so when we didn't have somebody pushing on it, F1 was enough to push it in a clockwise direction to balance gravity, which is pushing it in a counterclockwise direction. But once we get somebody pushing on the side of it, that is an added torque making it go in a clockwise direction. So this force needs to be reduced. Otherwise, the two torques here add up to more than the torque of gravity here. So that's why the author knew, just from that thinking alone, that they need to draw F1 a little smaller. Now, they also know that F1 plus F2 has to equal mg, so F2 needs to be drawn a little bit bigger. So if I come back to this picture and draw, F1 and F2 the same size, once somebody starts pushing on the side, this one needs to go down and this one needs to go up so that the two still add up to mg, but we have a torque from gravity matching the torque of these two, and that's why this one needs to go down in force, making this one go up. And remember, this one is right through the pivot, so as this one goes up, it doesn't change the torque at all. So this one can go up and up and up. In fact, I'm going to use that as kind of the concluding point there. All right, well, I've been doing a lot of lecturing, if you will, on thinking about torques, and hopefully that was helpful. Let's actually now get to the problem here. So the problem says a tall rectangular cabinet has 2 feet. It has a mass of 38.8 kilograms, so times G. It has a height of 1.93 meters. It has a width of 0.972 meters. It is pushed horizontally with a force of 146 newtons. If the force is applied at a height of greater than, so Y max, above the ground, the cabinet begins to tip over. So the key to this problem is what I was saying a few moments ago, is that the more torque you apply right here from this external force, the less torque we get from foot number 1. Or put another way, the more you push sideways here, the lower F1 becomes, which, of course, the greater F2 becomes. Now, I'll say it again. Since we're thinking about the pivot as being at foot number 2 here, you don't get any torque from number 2. This is that idea back here that the torque is the distance from the force to the pivot. And for force number 2, that distance is 0. So regardless of what force number 2 is, there's no torque. So again, if you're kind of thinking that torque then, or the sum of all the torques have to be 0, the stuff making it go clockwise, and so that would be the torque caused by this force and the torque caused by foot number 1 here, okay? Those are all making it go clockwise. And then the torque making it go counterclockwise. So for this problem, if this is our pivot, the torque making it go this way would be the torque of gravity. And that has to come out to be 0. So these two are negative. These two are the ones that make it go clockwise. The tradition is to call clockwise negative. So that's going to be a negative torque and a negative torque. And then the gravitational force, again, thinking of the pivot as number 2, is going to make it go clockwise. And so those three added together equal 0. All right. Now, you can begin to see that as I push more and more, this torque gets, magnitude-wise, gets bigger and bigger in the negative direction. This one doesn't change. This is the torque caused by the gravity. The force of gravity and the distance away doesn't change. But this one does. So this one goes down and this one goes up. And eventually, the most you can do is this goes all the way down to 0. And at that point, there is F1 equaling 0, which means F2 would have to equal to mg. Although I don't think that's necessary to solve the problem, because also keep in mind the first condition of equilibrium, that the sum of the forces have to be 0. So F1 plus F2 equals 0. So if force number 1 goes all the way down to 0, force number 2, all the weight of the cabinet is on foot number 2. So that's why I'm saying. Now, at that point, if you give it any more torque, either by pushing it harder or by pushing it higher, because remember, torque has to do with both distance and force. So if this outside force is either bigger or the height is either greater, giving it more torque that way, it will now tip, because the most counterbalancing torque we can get is this force of gravity. Now, I suppose if we made a kind of an artificial situation and we glued foot number 1 down, then we could actually have a force number 1 in the other direction if it was actually glued or bolted. Then we could begin to get a torque from number 1 that would be in the same direction as gravity, and therefore we could actually get more and more torque, either by height or by more force. But that's just kind of hopefully helping with your understanding that we can't have that. That's our limiting factor. This is a cabinet that the force can only go up. The force can't go down on foot number 1. It's not bolted or glued to the floor. So the most we can reduce force number 1 is down to 0. And so as the torque from this outside goes up and up and up, the torque from number 1 goes down and down and down. And that's the key to this problem. I'm going to set torque number 1 equal to 0. That right there would now make a position where the torque from the outside force is at its maximum, and it balances the torque due to gravity. That's the key to this whole problem. And so that's why I've been babbling on for the last 24 minutes here, trying to get you to understand the concept of equilibrium. the two conditions, and in this case, the torque one. And more importantly, how the torque can be calculated from any point, whichever makes it the easiest for you to think about. And in this case, I chose to do the torque around foot number 2, noting then that this torque, which is a clockwise torque, so it's a negative. Let me calculate it now. Let me use this formula for torque, R perpendicular. So if I draw a line across here, and the pivot is foot number 2, this is the perpendicular distance. Oh, I'm sorry, that's the height of the whole cabinet. My bad. The perpendicular distance is Y maximum. So I'm going to put Y maximum times the force of 146 newtons. And to make it the sign appropriate, I'm going to put that's a negative torque. That's a torque that if you can imagine holding it here and pushing it, it's going to make it go clockwise. And tradition is to call that the negative direction. We could change that, just like sometimes we change the traditional x-axis being positive to the right. Sometimes we call it positive to the left. But sticking to tradition here, because I don't see any advantage of changing, is I'm going to say then the torque from this outside would be the perpendicular distance times the force in the negative, and that would be the negative direction. Now, adding to it the torque of gravity, and so same logic. I'm going to take the perpendicular distance times the force. So here's the pivot, and so the perpendicular distance would be half the width of the cabinet. Again, assuming the center mass is in the middle of the cabinet. And so this would be 0.972 meters divided by 2. So there's the perpendicular distance. The amount of force would be its weight, so that would be 38.8 times 9.8. That's the force of gravity. And the torque would be a positive, because this one, if you kind of imagine holding it here and gravity pulling down, it would tend to rotate it in a clockwise direction. And that has to equal 0. And so, excuse me, the calculator work comes out here, and we can actually now solve this problem. So imagine this moving over to here. I'll just calculate this number, 0.972 divided by 2 times 38.8 times 9.8. So that's that force. Now, if I divide that by the 146, I get a height of 1.2, that's a 5, so I'll round it up to a 7 meters. And that's the maximum height, because any height greater than that gives it more torque than can be balanced with gravity. And hope that little mini lecture and calculation helps and wasn't too long. Take care.